Okay, I'll be starting off because time is of premium, and please let me know if you can see the screen.
So we can see your screen now. It's very pretty good.
Okay, great. So thank you everyone for that warm welcome, and it's a great honor to present at ODAC 2020, although it's a virtual one instead of actual physical one because of the pandemic, but nonetheless. My name is Soham Chakravarti. I'm currently a principal data scientist working in Noodle.ai, and I'll be going through something what we call as a spurious outlier detection system for high frequency time series data. And this is something we developed internally along with a few of my colleagues whose name are mentioned here. And this was an internal development work we did for Noodle.ai. So I will be very, very brief about Noodle.ai and what exactly we do. We are a US-based startup starting in 2016, so it's a little more than 4 years. And these are some of the details and recommendations and commendations from different organizations and global forums that we have received across the years. And typically, as a startup, product-based startup, what we do is that we provide enterprise solutions, enterprise AI solutions for manufacturing and supply chain domain. And we have our product suites. You can see here, Vulcan is for manufacturing and Athena is for supply chain. And each is divided into subcomponents, which tackles one particular or one set of particular use cases for that particular domain. And these are something that we offer to our clients, mostly enterprise clients, manufacturing, big supply chain organizations who have multifaceted, complicated problems that needs AI to solve. I work mostly in manufacturing, so that is Vulcan as product. And I'll be going through some of the kind of that we.
Sorry to interrupt you. Can you share this slide into full screen so that we can see it more clearly?
Yeah, absolutely, no issues. Better now?
Yeah, better. Thanks so much.
Yeah, sure. So these are some of the things that I will cover in this talk. I'll go through the introduction, the problem statement, and the conventional ways of thresholding and transformation to identify outliers in any system. And then I will propose two frameworks that we have developed, framework 1 and framework 2. So these are like iterations of the same original idea, but framework 2 we believe to be a robust and more improved version of framework 1, which we are going with now. It's in workflow. And then I will summarize with some concluding remarks and what are the areas that we have highlighted that can be improved upon in the near future. So just to give you an introduction, we deal with a lot of high frequency time series data. Seconds or even 1 second. So it's a huge volume. The volume and the quantity of the time series data is really enormous. That is the classical big data. And we were concerned with the anomaly detection part of the pipeline. That is, we provide to our clients anomaly detection, multivariate anomaly detection based on these sensor data and input. Now, how to differentiate between anomalies and outliers? Unfortunately, the standard literature that you will find Googling or any other open source forum will tell you that these are sometimes interchangeable. That is, the way we use the definition of anomaly and the way we call out outliers are sometimes very, there is no differentiating line. Line is very, very vague. But we, for our sake, need to make a differentiation. What we do is that we call out anomalies which are abnormal patterns which are coming from that multivariate time series data. The abnormality has to be defined in terms of a context. So it has to be a contextual anomaly, right? Outliers are basically, as the name suggests, and we all know about, rare occurrences in the data, which is very, very far from everything that we have seen so far. So it's a point which is lying completely outside the remaining points. And for our definition, for our purposes, what we saw was that outliers are typically coming from noisy sensor signals due to some sensor malfunction, due to some measurement error, some least count of measurement problem, or any other experimental error. I admit that these differences in anomaly and outlier are not very clear cut to some. That is something, unfortunately, we cannot do anything about. Typically, anomalies constitute less than 2 or 3% of the entire data. They are very, very tiny in scope and number. But what happens is that in the presence of outliers, the model sometimes confuses these noisy spikes in the data, which we are calling as outliers, with anomalies. And they are giving out what we call as false signals or false alarms. And sometimes this may even constitute 50% of the true anomalies that the model is actually giving as output. So what is happening, in fact, is these outliers are masking the true anomalous behavior. And we want to separate out the two. That is the idea that we started this work on. And this is the basic introduction that I can give you. The problem statement comprises of these 4 salient points. We want to develop a robust method that can identify contextual outliers in time series data, mostly high frequency time series data, but this is also applicable for demand forecasting or any other time series data. The method has to be scalable because of the volume and the quantity of the data that we have. It has to be scalable. The algorithm or whatever workflow that we design cannot exponentially increase in its complexity as the amount of data grows, right? And obviously the third point is something tied up to the scalability, that the algorithm has to be reasonably fast. It cannot take a whole lot of time to actually run. So it has to be fast, less expensive, because what we are doing is a very basic kind of identification protocol. This is not even a model training, but this is essential to our main workflow. And ultimately, we want to preserve the contextual information for subsequent analysis. So the points that we are flagging as outliers, we are passing them through in the later stages of our data science pipeline, where we are doing either unsupervised anomaly detection or supervised predictive maintenance problems. But we preserve that information so that we can differentiate, okay, these are my outliers, or my system has identified these as outliers, and these are my anomalies. Now, there has to be a trade-off between the two, and because this process is completely unsupervised, there's no way of telling what exactly is an outlier and what exactly is an anomaly. There's no ground truth. So we preserve that contextual information going downstream in the pipeline. These are the 4 problem statements that we are trying to deal with. Now, the classical method of outlier detection, I'll be very, very brief here. Everybody probably knows about it. Thresholding is a big part, so that you create some kind of upper control limit, lower control limit, plot your data points, whichever points is going above or below that thresholds. These are called out as an outliers. Standard way of doing it, as you have seen in the plot here, it's a mu plus minus 3 sigma kind of a method, which is very standard in statistical quality control. And it comes from the underlying assumption of a Gaussian distribution or a normal distribution. You plot the mean, you plot the standard deviation. Most of the points should lie between that 3 sigma line. Anything goes above or below that, you call it an outlier. This is a classical method, very, very conventional method. Everybody does it. But unfortunately, for our context, it does not hold true. Firstly, because the data that we see here, the censored data, is highly non-stationary. That is, the mean and the standard deviation, apart from the other higher order moments, these are changing with time. So you cannot expect a global thresholding to work. Whatever is defined as an outlier at time t might not be true at time t plus 2 hours because of the non-stationarity of the data. So this simple, sometimes naive, and very easy way of thresholding and finding outliers does not really suit our purpose. What about transformation? Transformation does help, definitely. If you transform your time series data into something more explainable, then sometimes it helps to accentuate the outliers, or you can spot them easier. Suitable transformation. It also acts as a variance stabilizing kind of a system. And we have given a very simple example here. This is a log transformation that I'm taking of successive uh, difference in log values of successive observations and then plotting that transformed value. And this works in specific context, but this also has its pitfalls, because if you do not take the transformation correctly, this can point out wrong outliers. As you can see in this example, in the circled red point, this point should not be an outlier. It is being called out an outlier because the transformation we have considered here, that is log of yt by yt minus 1, the difference between yt and yt minus 1, every time this increases or decreases, what happens is that the point gets accentuated, because I'm only comparing it with the previous point, which can be a good way of doing it under specific context, but not recommended all the time. So now again, transformation does help to a certain extent, but we cannot find a uniform transformation that suits our purpose. And we are looking for something which is repeatable across hundreds of thousands of sensors. which are continuously streaming back. What about taking them together? Transformation and thresholding. This is a very, very standard way of doing things, that you transform the data, pass them through a suitable transformation, and then use thresholding to actually flag the outliers. We have discussed both of them in very, very brief detail. And these are some of the things that you can try. We have actually tried all of these. There are statistical transformation of log based, and there are exponential transformation. There are different kind of transformation, delta transformation, everything. And there are also time series model based transformations, which is something like a smoothing technique, like an EWMA, or you can do some STL decomposition to iron out the trend of seasonality. You can use the EWMA on top of an ARIMA to get the white noise residuals or the IID normal residuals. And then you can use some kind of a 3 sigma thresholding or EWMA thresholding, or MAD, which is like the mean absolute deviation thresholding. And also there is a variation of MAD, which is double MAD. So you can use all of these in conjunction. But we couldn't find a method to actually tie all of these together. So what we propose here is an alternative approach. This is a framework. This is a workflow that we have constructed. Most of these pieces of this workflow that I'm going to describe here are not something that we have developed from scratch. These are all taken or all leveraged from existing techniques. What we have created is that we have rolled them out into one single pipeline, which can be executed over and over again, which is scalable, which is fast, and which has been found to be quite robust enough across different kinds of sensors. Now, what it comprises, this is the approach one that we had developed before. So you have the data in module, where the data comes in univariate level, univariate time series, no R. Then the change point detection comes into picture. So what is change point detection? You detect sudden changes in the distribution of your incoming data. It can be a mean shift, it can be a variance change, it can be both. Why change point is necessary? Because if you do not use the change points, then the points which are lying in, let's say, zone 1 before the change point happened versus the point which is lying in zone 2 after the change point happened, these two are not comparable. We cannot make an apple to apple comparison between the two. Without the change point, there is no way of saying that. So we need to find a way of differentiating these kind of sort of homogeneous distributional chunks, which are defined by these change points. Once the change point detection is passed through and we identify what are the possible change points, we use a simple EWMA smoothing technique. There can be, you can use anything else. We are just proposing this on every chunk of that data. So if you have like 3 change points, so you will have like kind of 3 separate big chunks of data which are supposedly similar to each other in distribution, and you use the EWMA on each of these chunks separately. So we are not overlapping between the two. And these are used on a sliding window basis. Why sliding window? Because as I described before, global thresholding does not work for our case. Non-stationarity has to be taken into account. So you use a sliding based window based method, where the size of the sliding window is again a hyperparameter that is left upon the user to choose. If you take it too big, you might have some other problems. If you take it too small, you might catch some really local outliers which are not really does not have any sense. So it has to be tuned judiciously, but it can be done. Once you do the EWMA thresholding, you will get a lot of local outliers. So for every sliding window, you will probably catch 1 or 2 of these points as outliers. Now you will get a lot of points across your entire data. Not all of these can be outliers. What we need are those points which are actually global outliers, which are basically outliers even among those local outliers. So here we are proposing to use a kernel density and skewness based filtering technique. I will go through each of them in brief details. And then once this part is done and we identify those points which are passing that stage, we will do a data out kind of a system where the original data that you pass on will be outputted along with a new column or new series, or however you want to say it, with an outlier flag, which is basically a binary flag, that is this point is an outlier or not, 0, 1 value. This is the framework. Now, as I described before, change point detection is necessary. This graphical illustration just shows the point that in case of this kind of a data, you cannot assume that all of these data are coming from a single distribution, or there is no shift in that, in the moments of the data. So we are doing the change point to identify these breaks, possible breaks in the data. And EWMA is a very, very well-established techniques. I don't have the time or scope to go into much detail about this. But I'll just describe that this is a smoothing technique. It smooths the data, and then the degree of smoothness can be controlled using a lambda parameter. That will give you the how much smoothness you want in the data. Kernel density as skewness-based filtering is just we are basically choosing those local outliers which are extreme among the local outliers. We're using the kernel distribution. Skewness is done to select which tail is heavy. Is it a left tail distribution? Is it a right tail distribution? And we're doing a skewness test on the sample skewness value, check if that value is again significant, statistically significant or not. And these are some of the examples from real data. These are actual live industrial manufacturing data. You can see the examples. The red points are highlighted as change points, the outliers, and the change point are at the bottom left plot, which are marked as vertical dashed black lines. And the second framework is basically an update on the first framework. It's almost the same. We are doing the same steps. Some of the filtering is done differently, and we are improving upon these two modules. One is the change point part, which is we are using some algorithm called regime shift detection, which is based on a paper. I'll show you the bibliography of that. And we're also using a k-means kind of a sliding window outlier detection instead of doing an EWM based technique, which we found to be a much more robust and everything better. In every way, it's a better technique. So not all kind of signals that we face requires a change point. A lot of signals are like without any distributional changes. So we have added a preliminary test module which will check for incoming data whether change point detection is necessary or not. The regime shift detection, as I have discussed here, is based on change point detection based on t-test. Anybody willing to see, go look at the paper, you can find it open source. And we're using that instead of our earlier approach. And we are using a potential upgrade to detect outliers based on the neighbors called the key neighbors based method, which is again, we hope as an improvement of the EWM method. And these are some of the examples, again, based on real life data. These are data from South American steel mills. The sensors without the outliers are on the left, with the outliers, red points are on the right. And you can see that these flaggings are being done locally, but we are only showing you the global outliers. That is after doing that skewness filtering and kernel density filtering. And these are again some of the change point based example. The intensity of this yellowish kind of a color increases as you go from left to right, which indicates the different chunks of change points. And we are using this algorithm on every homogeneous chunk separately, as I've described before. This is again a real sensor data example. And this is again some examples. We have added some examples just to show you that this can be done. Just to show you that without the performance of this two approaches, the second approach is much, much faster. Quite fast. This is actually done. This simulation was, or this experiment was run on 1.7 million rows of data, approximately, which is a considerable amount of data. And we have seen that it scales. Even if you increase that number to 5-fold or 10-fold, this numbers does not really change. But our earlier framework was much comparatively slower. It was not computationally efficient. So this is again a very nice upgrade that we have. I'm not going through the summary. I think I'm almost run out of time. The further areas of improvement that we are working on is that to modify the change point detection to make it even more strong, because it's sometimes very sensitive to the kind of data we get, or any minor fluctuations of the data can change the results. We are working on that. We want to combine the results more efficiently with anomaly detection techniques to infer about the data better. We want to create a suitable metric to gauge the efficiency of the outlier detection technique. We don't have that currently. We are working on it, but it's quite difficult without any ground label truth. We don't know what exactly constitutes an outlier and an anomaly. It's a very confusing kind of a distinction anyway. But we're trying to create some kind of a metric, even though it's very simple, but we need a number to actually say, okay, this works or this does not. There's a work in progress. Along with the multivariate extension of this. Right now we are doing it at a univariate level, which is good, but we want to create a multivariate extension, but this is a very tricky problem to solve because multivariate change point detection is notoriously difficult. Again, these are some of the things that we hope to show you the next time ODAC comes in, hopefully physically. Till then, it's a work in progress. And these are some of the references that we have used. I think I've shared it already. So anybody wants to see which are the documents or papers or journals that we have used, you can find it there. Most of it is here. whatever we use. These are all open source and publicly available. Thank you for your time. I think I'm almost done here. Yes, I just crossed 1 minute. Thank you for your time. Any questions that you have, I'll be glad to answer in the channel itself. Any feedbacks are most welcome. Thank you. Thank you.